Alright, we've made it to the last lesson of Unit 6. It's Lesson 8.6. And you thought that we were done with convergence and divergence? Well, think again. We will be after this video. But we have to introduce to you two new terms. Something called absolute convergence and conditional convergence. And we'll show you what those mean and how they differ. So, in this lesson, we're really talking about convergent series that have negative terms. So, just something like this, right? 1 minus a quarter plus 1/9 minus 1/16, etc., etc., etc. Okay? Alternating like this, or some other pattern where a whole bunch is negative, then it's positive, then negative, then positive, vice versa. Well, if I were to take the absolute value of each of the terms, so making every term that's negative positive, notice what happens. Well, it really makes that new positive series, that's one in red, less likely to converge. Well, why? Well, I think you can think about this and think about it well. The sum of the terms in red will definitely be larger than the sum of the terms in blue. So if the new positive series is still convergent, so if the red one is still convergent, then the original series is called absolutely convergent. Okay? If, on the other hand, the new positive series, that red one, is divergent, well then the original series with the negative terms is still convergent, but it's called conditionally convergent. So to summarize once again, if a series converges after taking the absolute value of its terms, it is guaranteed to also converge with no absolute value. And that's why we call this absolutely convergent. So let's tackle these three examples to show you how this can be done in action. Determine whether each of the following series is absolutely convergent, conditionally convergent, or divergent. So the first thing you do is look at the series originally and say, hey, is it convergent? Yes or no? Well, looking at this one, we know this is a negative 1 to the power, so it does look like it's alternating. Okay. We know that the terms in absolute value decrease, right? Because you just get 1 over n, so 1/2, right? 1/2, 1/3, etc., etc., etc. Of course, that's smaller. We can also say that the limit as an approach to infinity of the terms, what will that become? Well, that approaches 0. So therefore, what we can say is that the sum of n equals to 1 to infinity of negative 1 to the power of n over n converges due to what series? Yeah, because it's due to the alternating series test. By the way, this is the special series. It's an alternating harmonic series. Okay, so we proved that the series converges. That's great. So now let's see if it actually absolutely or conditionally converges. So now I'm going to have to take the absolute value of the terms in this series. This just naturally becomes the sum of n equals to 1 to infinity of 1 over n. This, I hope you understand, is the p value of 1. This is the harmonic series, and we know by the p series test that this is divergent. So, what can we say then about our original series? So, our original series with the alternating terms was convergent. Once we took away all those negative signs, we showed that this is divergent. So, therefore, we call our original series conditionally convergent. There we have it. Okay. Number 2. Well, cosine. You know cosine fluctuates from positive to negative to positive to negative. So this is not an alternating series, but there are negative terms. Well, how do we show if this thing is actually convergent? Well, I'm going to use a comparison this time. So compare it to what? Well, I know cosine goes between -1 and 1, so I can just say that let's compare it to 1 over n squared, since I know all the terms of cos are less than or equal to 1. Notice in this case the p-value is 2, so by the p-series tests, we know that this must be convergent. But that's 1 over n squared, not cosine n, so I guess we should be comparing. And once again, I know that cos n squared is definitely less than or equal to 1 over n squared. So, by the direct comparison test then, I should know, or I do know, that the sum of n equals to 1 cos n over n squared is also convergent. Okay? Now, the question is it absolutely convergent or conditionally convergent? So now, if I were to take the sum of n equals to 1 to infinity of the absolute value of cosine n over n squared and try to figure that out, well, notice that the absolute value is still going to be less than or equal to 1 over n squared, which is really what I just did up here, right? So I can say by the direct comparison test again, I know this series also converges. So the one with the negative terms converges, the one with the absolute value of those negative terms, meaning they're all positive, also converge. So therefore I'll say that the sum of n equals to 1 to infinity of cos n over n squared absolutely converges. Alright? Does that make sense? See the difference between the two of them so far? Alright, so last one, numero 3. The sum of n equals to 1 to infinity of e to the power of n over n to the power of e. Interesting. What happens when I take the limit as n approach to infinity of that? So we have here e to the infinity. That's really infinity. Infinity to the power of e is also infinity. So what's up with this? L'Hopital's rule, friends? You could. Or you can use that growth model here. So e to the power of n grows to infinity pretty fast. Infinity to the power of e, that's still infinity, yeah, but that's much slower. So knowing that we have this, our final answer will most likely be infinity. This is definitely not equal to 0. So by the nth term test, I've shown that this series diverges. And if it already diverges, who cares about taking the absolute value of those terms?